This course will cover industrial digital isolation. In this course, we'll talk about the need for isolation in electrical systems, explain Maxim isolation technology, and the benefits of digital isolators. Isolation is a means of preventing conduction between two parts of a system, while allowing signal and power transfer between those two parts. Isolation is required in an electrical system for a variety of reasons, which can be simplified into two situations. In high voltage systems, isolation is used to prevent current surges from damaging equipment and to protect humans from the mains voltage. In analog subsystems, isolation is used to break ground loops where different ground potentials are involved. There are many different ways to isolate the data. Physical isolation is the most basic form of isolation, which means a physical barrier is placed between inputs and outputs. This can be insulation material, an air gap, or any non-conductive path. However, the signal of interest must cross the isolation barrier. Therefore, we must have a transfer or coupling of signal energy across the isolation barrier. Optical isolation uses light to transmit information across the barrier. Typically, a light-emitting diode, LED, transmits information to a light-sensitive receiver, for example, a transistor. Transformer isolation technology uses the inductive characteristics of transformer coils to transmit a signal across the isolation barrier. Capacitive isolation uses capacitive coupling to transmit a signal across the barrier. Semiconductor material-based capacitors, such as silicon dioxide or polyimide, are used as the isolation component. There are two architectures used with capacitive isolation: edge-based and on-off keying. The edge-based method encodes rising and falling edges as different pulses, and on-off keying transmits a carrier frequency when the input is high and does not transmit when the input is low. Here is a summary of different isolation technologies. For optical isolators, the advantages are thicker insulation for fail-safe applications and high working voltage. The disadvantages of optical isolators are slower data transmission rates, relatively high power dissipation, large performance variation over temperature, LED degradation over time. For inductive isolators, the advantages are inherently good common mode transient immunity, or CMTI, and low power. The disadvantages of inductive isolators are they are susceptible to EMI and EMC interference and consume higher power at high data rates. For capacitive isolators, the advantages are fastest data transmission rates up to 150 megabits per second, good immunity to EMI, EMC fields, low power at low and high data rates. The disadvantages of capacitive isolators are they are susceptible to electric field interference, and they require extra circuitry to have good common mode transient immunity performance. Maxim's isolation products use edge-based capacitive technology, giving the best performance in terms of lowest propagation delay, lowest jitter, and lower power. This slide shows the advantages of Maxim digital isolators over optocouplers. Faster propagation delay. The Maxim digital isolator has a maximum of 7.4 nanoseconds delay compared to 22 nanoseconds with the optocoupler. You also get lower pulse width distortion, 1 nanoseconds with Maxim versus 2 nanoseconds with the optocoupler. Lower propagation delay skew. The Maxim digital isolator has only 3 nanoseconds of skew compared to 16 nanoseconds for the optocoupler. Lower current consumption per channel.
The maximum digital isolator consumes half the current of an optocoupler. And better common mode transient immunity. The maximum digital isolator features 25 kilovolt per microsecond CMTI compared to the 10 kilovolt per microsecond of the optocoupler.
This slide shows the key specifications that should be considered when selecting an isolator for the system. We will talk about the definition of these specifications and the relationship between certain specs. A wide variety of standards exist that are related to isolation at both the system level and component levels, for different geographic regions and for different applications. Different regions in the world determine their individual standards, and an organization in that country issues approvals or certificates for the equipment or component. For example, UL in the USA, CSA in Canada, VDE in Germany, and CNCA in China. IEC, the International Electrotechnical Commission, is the organization that publishes the international standards for electric system safety. Equipment safety standards apply to an end equipment which is assembled from multiple components. These standards cover the safety concerns, including isolation, pressurized gases, and strength of electrical cords. These standards do not specify an isolator, but are related to an isolator because they specify the transient voltage, creepage, and clearance for the insulation. An isolator to be used in the system must comply with these specifications. Component certification standards apply to specific components that can be used in a variety of applications. These standards define the required tests, sample size, and preconditioning. They may also define terms and information that are required for the datasheet. During normal operation, the stress voltage across the isolation barrier is limited by the maximum system line voltage. However, unintentional disturbances in the system, for example noise on the supplies caused by arcing or load changes, could briefly cause the voltage across the isolator to be several times the line voltage. The isolator should be able to handle these transient overvoltages without damage. VISO is defined per UL 1577 as the RMS value of voltage that the isolator can handle without breakdown for 60 seconds. It is tested during certification by applying a sinusoidal stress of VISO for 60 seconds. VIOTM is defined as the peak transient voltage that the isolator can handle without breaking down. In production, VISO is tested by stressing every device by applying 1.2 times VISO for 1 second. For sinusoidal stress, VIOTM and VISO are equivalent. The working voltage rating of an insulator is the continuous voltage that could be placed across the insulator without failure. VIO-RM is defined as the maximum repetitive peak voltage that an isolator can withstand. VIO-WM is defined as maximum RMS or DC voltage. For sign stress voltage, VIO-RM and VIO-WM are equivalent. VIO-SM is the surge voltage rating for protecting against high voltage transient events. As per IEC and VDE standards, an isolator claiming a certain VIO-SM must pass the surge test at a peak voltage of 1.3 times VIO-SM for basic isolation and 1.6 times VIO-SM for reinforced isolation. An isolator can be called reinforced at the component level only if it passes the surge test at a level greater than 10 kilovolts. Creepage is defined as the shortest distance between two conductive materials, measured along the surface of the insulation. Tracking is the process that produces a partially conducting path of localized deterioration on the surface of an insulating material as a result of electric discharges on or close to an insulation surface. Tracking damage in the insulating material normally occurs because one or more of the following reasons: humidity in the atmosphere, presence of contamination, corrosive chemicals, and even the altitude at which the equipment is to be operated. The degree of tracking depends on the Comparative Tracking Index, or CTI. CTI is an index used for electrical insulating materials that is defined as the numerical value of the voltage which causes failure by tracking during standard testing. The higher the CTI value of the insulating material, the smaller the minimum creepage distance is required. Clearance is the shortest distance between two conductive materials measured through air. As with the creepage distance, the amount of pollution, the temperature, and relative humidity influences the tendency for a breakdown. Breakdown along a clearance path is a fast phenomenon, where damage can be caused by a very short duration impulse. Therefore, it is the maximum peak voltage, including transients, that is to be used to determine the required clearance spacing. All isolator datasheets should have a table to specify insulation specifications. The key specifications are shown in this electrical characteristics table. One of the key specifications of isolation technology is common mode transient immunity, or CMTI. It quantifies the ability to tolerate fast changes in the potential difference between two grounds, common mode, without causing bit errors. It is measured in kilovolts per microsecond, and a high CMTI indicates a robust isolation channel. Maxim's digital isolators both isolate and provide voltage translation between two domains. It is important to remember that the products are specified with a maximum data rate in megabits per second, which is not the same as the system clock rate in megahertz. Key specifications for electrical performance are propagation delay and skew, which is provided for channel to channel and part to part. Voltage translation resolves different voltages for digital and analog ICs. The data rate specification is important for high-speed SPI interfaces. Propagation delay is critical where the round-trip delay adds to the timing budget. Propagation delay skew is critical if the timing budget relies on matching between channels. For example, the clock is transmitted on one channel and data on another channel in the same direction. Glitch rejection, using the integrated glitch filter, increases propagation delay and reduces the data rate, but improves operation in noisy environments. Power consumption is determined by voltage, data rate, and the capacitive load. Voltage translation is important when interfacing products such as a low voltage microcontroller and a higher voltage peripheral. Timing is important for higher speed SPI buses. Traditionally, SPI clock rates were 5 to 10 MHz, but peripherals such as ADCs often need clock rates up to 75 MHz. The isolator creates additional signal delays for the SPI bus. The master uses the rising clock edge to send data, and the falling edge to sample the data sent back from the slave. The system designer needs to check the timing budget to be sure the isolator propagation delay does not violate the master's timing requirements for sampling on MISO, or the master loses synchronicity or introduces errors in the received or transmitted data, as shown in the timing diagram. Consider the circuit arrangement shown here, which is typical of isolated high-speed SPI communication between an FPGA and an ADC. The ADC is isolated from the FPGA using the MAX 14935 isolator as shown. S-clock is used to clock data from the FPGA to the ADC. At the input to the ADC, the isolated S-clock is represented as clock and the isolated MOSI is represented as DN. This arrangement is only possible if propagation delays introduced by the isolator and the skew between the respective channels of the isolator are both extremely small. In low-speed SPI communication, the master clock would also be used to clock data traveling in the reverse direction. However, in order to compensate for the fact that the master clock has already been delayed by the isolation in the forward direction, it is better to return a copy of the isolated S clock, shown here as clock, when clocking data in the reverse direction from the ADC to the FPGA. This ensures that the timing of clock and D out are still in sync by the time they have been isolated and reach the FPGA as return clock and MISO, respectively. In order for this arrangement to be successful, it is essential not only to have low propagation delay and low channel-to-channel skew, but low part-to-part skew is also critical. Here are examples of Maxim digital isolators. The MAX 1493X and MAX 1293X family of parts are based on Maxim's proprietary capacitive isolation technology and are intended to provide system designers with the highest degree of flexibility when incorporating digital isolators into their designs. Some features of these parts include high isolation voltage, up to 5 kilovolts RMS, data rates up to 150 megabits per second, wide supply voltage range, typical propagation delay of 5 nanoseconds, maximum pulse width distortion of 1 nanosecond, maximum channel-to-channel skew of 0.9 nanoseconds, and maximum part-to-part skew of 3 nanoseconds. The MAX 14933 and MAX 14937 bidirectional digital isolators both provide two bidirectional open drain channels for I2C buses to isolate SDA and S-clock signals. The MAX 14933 has 2.75 kilovolt RMS isolation voltage and is in a 16-pin wide body and 16-pin narrow body package. The MAX 14937 has 5 kilovolts RMS isolation voltage and is in a 16-pin wide body package. Both devices support I2C bus speeds from DC to 1.7 MHz. These devices are another example of Maxim's second-generation technology, featuring improved CMTI and lower power consumption. These parts are two-channel products with 2/0 and 1/1 options targeting GPIO, UART, and RS-485 transceiver applications. Key benefits of these products are improved CMTI of 50 kilovolt per microsecond, which improves system noise immunity, best-in-class propagation delay under 8 nanoseconds, 0.65 milliwatt per channel at 1 megabit per second with VDD equal 1.8 volts, a wide voltage range available, and 3.75 kilovolts RMS of isolation in an SO8 narrow package, and 5 kilovolts RMS of isolation in an SO16 wide package.
In this course, we have talked about the need for isolation in electrical systems, explain Maxim isolation technology, and the benefits of digital isolators. For more information, please go to our website at www.maximintegrated.com under Products, Interface, and Isolation. We hope you enjoyed this video and see you next time in another educational video of Maxim Integrated.